Hey, what's up, guys? Yeah, today I want to talk about another complexity theorem, and I feel it's interesting, so I'll share with you guys. Called Savitch's theorem. I think this is yeah, so 1970. Okay, so basically story I should say is that we want to understand the space, non-deterministic space, and the space complexity, or the deterministic space complexity. So we know there is a non-deterministic term machine and a term machine, deterministic term machine. The deterministic term machine is the transition function between the deterministic term machine is a function, and for non-deterministic term machine is it's just the relation. Okay, so non-deterministic. So for deterministic term machine, then your computational branches must be deterministic. For non-deterministic, that there's a maybe some points that you can like have the different branches. And the non-deterministic will very smart. If there's a way to make the term machine accept, then you will accept. Okay, so we want to understand the space complexity for the deterministic and time-deterministic. Okay, so one famous, the one for time, right? If you ask about time complexity, then this is the biggest open problem, right? Where p equals to p or not. Okay, because we don't really know that the deterministic term machine. So we don't really know that the only thing we know is that right. So let me just write down. So one can define time, right? So this is the deterministic term machine, the language that you can solve in the deterministic term machine in f of n. The one can also define non-deterministic time. Okay, and obviously that we always have this. Okay. Okay, and we can define P to be the union of this guy, right? To the K. Okay, and we can also define NP. Another way to define NP is just using this, right? We can define non-deterministic machine and solving them to the K. Okay, and obviously that from this definition, that we always have that P is the subset of NP, right? But we really don't know where there are several. Okay. So interestingly, that we can do the same thing, right? For space, right? So one can define one can define P space, which is a deterministic term machine by using only polynomial space. You can define deterministic term machine P space using n to the k. Sometimes there's people will omit this d. Okay, so we need a k, and the one can also define a P space to be the k of n space. So basically, non-deterministic term machine, but only using the point space. Okay, and the theorem, which is the Savitch theorem, will implies that P space is actually a P space. Okay, so this is the introduction story. So let me just talk about the reason. Okay, the theorem is say you consider S, n is the function which is space constructible, so it's greater than of n. Your n space f of n is in the D space f of n squared. Okay, notice that this is true, so immediately implies that P space is equal to n space, right? Because by definition, right, you already have D space f of n is larger than the D space f of n, right? So but each n to the k is bounded by another n space, and each n space n to the k is bounded by a square of D space. So you write down the two sides inclusion. Then you immediately prove that if this is true, so you prove that n space goes to P space. This is trivial by this definition. Hopefully you can immediately see this. Okay, and this is the first one. Another implication is that one can define NL. So NL is basically the n space. The problem that you can solve in n space, but only use the log n. Okay, and the fact is that this NL is Yeah, so basically it's analysis in a D space of log n squared. Okay, and there's a way to prove this. I see. Okay. Yeah, I will prove this in a minute, but this is not difficult. Okay, so let's prove this. Okay, so in order to prove this, the standard idea is just use the reachability. Okay, so okay, so this is a fact, right? So given that G is what is it? An edge, and then let's say G is directed or the graph. Actually, it probably doesn't matter, and then we pick SNG. Okay, so people can start the problem called Eon SD. Okay, so Eon SD or connectivity ST basically is that true if S and T are connected. Right, there's a way to start from S and go to T. Otherwise it returns false. And obviously that one can solve complex T, right? In the let's say the number of vertices is n in time using BFS or DFS, right? So basically, if you can solve indeterministic time using linear timing, right? Because you can use BFS, right? So each of time that you reach some vertices. Okay, so but the Savitch's theorem, Savitch shows that one can solve complex T in Polish space, in normal space, or normal square space. Okay, so basically what is things that complex T is in D space log n squared. Okay. Yeah. Okay. So in order to prove this, we can just do a very yeah. So the rest is just the standard textbook results. Also, we can just write an algorithm called reach. And then there's a this idea just say that there is a path. So it's just return true if there is a path from ST with length L. Okay, so the notation if L is 0, then T must be S. Okay. Okay, so yeah, so yeah, so if L is 0, yeah, so yeah, L is 0, so you just return whether S T equals S. Okay. So if L is 1, then you can just return that whether ST right is in the edge. Okay, because there's only one start from S and then there's only one T. Okay, and else, right? So else that like for all W B, right? You just solve. Let's say you can solve this reach SB sorry SW and let's say L divided by 2, and you solve reach W and T L divided by 2. Okay, so basically it's true. So this means that by things as it, so you use dynamic programming, right? So if S goes to T, there is a TW that the length is less than L divided by 2, and this is less than L divided by 2. If these two are exist, then there must be a path for S. Okay, then if this is true, then you return 1. Right? Means basically you do this. If you cannot find such W, that means there is no such path. Right? So I'll find you just return. Okay, and then we can write the space complex for this. Okay, so this space long is powerful because is very small, right? The reason is that you just need to iterate all this this paths, right? So you need the log n, and like for each of these half, right? You just delete. You're just using the half. Each you have that's the binary search, right? So log n is for this v, and for each v, right? For each w, this always just run the at most log n, right? So total complexity is log n space. If you draw a path, then you can see, because this iteration will take some space. Okay. So it's log n space. Okay. Once you have proved this, then you finish. Basically, you finish the proof, right? Because in the non-deterministic machine, you're non-NTM, right? So now we can prove this by just simply using the Savitch's result. Because for non-deterministic machine, then you have branches. You have such branches. You have such computational branches. Okay, and since you're at most use f of n, right? So you at most use f of n, right? So after you accept, and the number of vertices at these branches is basically f of n, right? It's at most, because after, if there's a branches such that you can do it, right? That this most oh, sorry. Okay. So if the space is f of n, then the number of total nodes that you can use is like 2 to the c to f of n. Sorry, I'm stupid. Yeah. Right, because you need to, because like 0, so you can store like 2 to the c to f of n of these nodes, right? And by our results, but is if you change it, but you can solve this using deterministic, right? Just reachability, right? So you start from here, and then you ask whether there is a Q accept, and you check whether it's doable or not. Okay, so you can solve this in, just I said, right? Log square v in a deterministic space by just using the reachability. Okay, so yeah, so basically this is just plug it to just f of n square. Okay, so yeah, so this is the proof, and yeah, that's whole proof, and yeah, hopefully, yeah, actually one can show that this connectivity is like NL complete, but maybe I will talk in the next video.